Hi, welcome back. In this lecture, I want to discuss quantum feature maps. In particular, I want to look at the quantum circuit architecture to describe quantum feature maps. Before starting with the full content of this lecture, I want to have a brief recap of what is a feature map. A feature map in quantum computing and quantum machine learning is nothing else than a quantum circuit that takes our input vector and prepares into quantum state. More formally, a feature map is defined by a parameterized circuit called phi. It's parameterized because it contains gates that depends on parameters, for instance, angles, and is acting on an input feature vector called x. Our parameterized circuit depends on the original data because it takes as an input of these parameterized gates and therefore can be used to prepare a quantum state that depends on our input feature vector. A feature map also can be taught as an encoding technique. So we go from a classical description of our data into a description that you use in the quantum state. So it's a sort of encoding. You also hear talking about quantum embedded technique. That's also another name you will hear talking about feature maps. It's basically the same thing. So in summary, our feature map circuit, it takes our input classical data as encoding in some parameters of our quantum gates within the feature map circuit. For instance, some angles. It's important to realize that our quantum circuit are all initialized to 0 or to a classical state. So differently from the classical technique where we initialize a circuit directly with the data, in this case we initialize the data in one classical state, for instance all 0, and then we encode our data into the parameters of the quantum gates. So let's start with the first technique for encoding or feature maps, and is called angle. So in this case, we are using we have our data set that has n scalars. So our item or our sample in data set has n as a dimension. So this will be described by n scalar vector for each of the feature. So if we have n scalar for n feature, this will correspond to n single qubit rotation on n qubits. We can use rotation x in the Bloch sphere. We can use rotation y in the sphere. If we want to use RZ, we will need to add another NAND gate here before that. So the way to do that, we initialize each qubit in 0, and then we take the feature 1 value and we include as a parameter of the first qubit of the first rotation on the first qubit, and then we take the second value of our feature input data, and we put as a parameter of the second rotation on the second qubit. I can do this, so forth, and so on. You can really understand if we have n dimension in our input vector, then we will need n qubit on which one we are going to rotate, maybe Rx, Ry, and then we include this data as a parameter of this rotation. This quantum circuit is simple, it's very shallow, and it's very hardware friendly because technically you just need one gate for each parameters. So the way to think about is in think local sinusoidal features for a variable. So you can think as a local sinusoidal feature associated with each variable. There is no entanglement by default. So there is no control knot operation. There is no control operation connecting different qubits. So entanglement cannot be realized. However, we can include some additional control gates in order to include some entanglement. This is typically a very good first baseline when we start with the feature maps, and is very good when variables contribute mostly independently. So there is no correlation between different features in our dataset. As I mentioned before, we can also add entangling layers later on if interaction structure matters. So if we realize that there is some interaction between the different features, it might be good to add later on some control operation to add also a capability of entanglement. What are some of the issues? Well, an important issue about angle encoding is that normalization is very important, and because we are dealing with the rotation and we are encoding our data as a parameter of rotation, then this rotation display periodicity. What it means is that 0 and 2 pi are basically the same angle, and therefore they're going to map to the same quantum state. This is also called extreme, aliasing of extreme, because you can see that 0 to pi, but also 4 pi will be mapped basically to the same state. So we can have a wider range, for instance, from 0 to 4 pi, but this will span more feature space, but with the risk of aliasing. That means that different values will be mapped exactly in the same quantum state. So that's a typically problem of this encoding. So we need to be quite careful about the range of our data and how we normalize, because there is this issue of the periodicity. As I mentioned, one of the major advantages of this is the depth is very shallow, maybe 1 or 2 if we use some other Hadamard gates and rotation in the Z on the blocks sphere. A second technique is called the amplitude encoding. In this case, we are going to use the amplitude of the quantum state vector to encode the values of the different features within one vector. So what it does, it maps a length 2 to the n vector x, this is our input vector, to a quantum state called psi of x, where each amplitude depends on the particular values of that feature, which is also normalized over the basis state. What is the good things about this? Well, we are using all the 2 to the n basis states. So differently from the angle encoding, where we need for n feature, we need n qubits. Here we can use the full range of the quantum state. So for instance, if we have 8 features in our dataset, this corresponds to 8 dimension. In the case of angle encoding, we need 8 qubits. In the case of amplitude encoding, we just need 3 qubits, because we can use the 2 to the 3 quantum state. One of the issues is that for instance, we have a vector that is all 0, and this will undefined. And other things that normalization is also required. So as you probably understood after this very brief introduction about amplitude encoding, one of the major capability of this feature map is the massive capacity. So by just adding 1 qubit, we are basically doubling the capacity of expressing new data. However, the loading of the data is non-trivial. What does it mean, the loading data is non-trivial? Well, it means that the quantum circuit is quite complicated. So if we want to use a quantum circuit to do this operation of taking the input vector and transform and map to the different amplitude of the state vector, then the circuit is quite deep and complicated. So this requires some specialized quantum circuit. It is implemented in penny lane. So for us, it's just one function. However, if you want to then realize on and run on quantum hardware, we will need quite a deep quantum circuit, and you will need to pay the cost for doing this encoding. So for instance, there is this very important paper describing the basic technique to encode amplitude that goes under the name also of the first author in this paper, Mototan transformation of feature map is nothing else than amplitude encoding, and you see here a diagram of how to implement and this basic primitive decompose in a quantum circuit. As you can see, it can become quite deep. So this map is great for compacting high-dimensional vectors when state preparation is available, but the state preparation is costly. Obviously, it would be very nice to have a quantum RAM, quantum memory, so we can have already the data encoding in the amplitude, but this is difficult to achieve. So we need to rely on some quantum circuit to prepare into the amplitude encoding. I want to say a few words about an important feature map called the ZZ that is relying on the so-called ZZ gate, or also called the Ising ZZ coupling gate. So this is a 2-qubit entangling gate that applies a phase shift depending on the state of the 2 qubits. So it's a 2 qubits quantum circuit. It has control knot operation that is sandwiching a rotation in the z direction in the Bloch sphere, and then is taking our parameter, which is our input vector, as input vector element as a parameter of the quantum gates. So this is implemented by combining two single qubit control Z gates and use to create entanglement between the 2 qubits. It can be set with a single parameter, theta, which determines the strength of the entanglement. What is the intuition? Well, so this, whenever we have even parity, so 2, 0 or 2, 1 in the B strings, then we'll be shared the phase. However, when we have odd parity, so different values in the B string, this will get the opposite phase. This is a very nice way to encode a pairwise structure into the encoding. So if we have data, we know that there is a relation between pairs of a feature. This is something that we could use for our feature map. So this is a basic gate. We can design a feature map that is relying on this ZZ gate. So these have a formant abstraction. There are different steps to construct a feature map. I just show you here a ZZ feature maps on 3 qubits. They all start with Hadamard gates, and then there are some local RZ rotation, and then we have 2 pairwise entangling layers. So the first one entangling the second qubits to the first one, and then another one entangling the third qubits to the first one. So these pairwise entangling layers, they use ZZ style rotation, and note also that we are including our data here. Not only here, so these are basically an angle encoding, and then we add additional encoding of the angle using this ZZ style rotation. This is implemented in Qiskit machine learning. In PennyLane is not implemented, but is doable to do it. And actually we show in the next lecture, we write also code and provide you in Canvas. So what are the basic intuition? Well, this is rather symmetric feature maps that the phase depends on the joint parity of the qubits, and it's quite useful when interaction between variables drive the target function. As for the angle encoding, we need to be careful with the normalization. There is a similar trade-off as angle encoding. Choose wisely the range, like 0, 1, or 0, 2. Too wide range risk the phase wrap up around this aliasing problem, and too narrow reduce the expressivity, right? So we don't use all the expressivity. It's good to use it when we suspect the data has a very strong pairwise interaction. So we believe that there is some correlation between different pairs of the feature input, and also is a kind of expensive in terms of angles. It requires n to the square entangling terms, so it tends also to be deep, increasing the number of qubits. However, it's really a mid-ground between simple angle maps and more heavy amplitude maps. There are also other feature maps that you might encounter during your study. There is a very famous one called IQP that stands for Instantaneous Quantum Polynomial Time feature maps, and is the one that is used in this seminal paper introducing also quantum support vector machine, supervised learning with quantum enhanced feature space. So the IQP feature map is a circuit where data-dependent middle blocks consist of a commuting Z-type phase operation, which has been sandwiches between Hadamard gates on all qubits. So if you are interested in that, I strongly recommend to read this paper here. There are also feature maps that try to encode some graph structure. These are called graph state. So this we pick a graph of qubits and place control Z gates on its edges, and then prepare uniform superposition Hadamard gates on all qubits, and then add small rotation before and after the control Z pattern to inject data. If you're interested in this, also recommend this very important paper here on the slide. These are the last slides of the lecture. Talk to you soon.